Imagine an object so powerful that it can swallow an entire star, bend the path of light, distort time itself, and create a region of space from which nothing can escape. It sounds like something from science fiction, but these objects are real. They are black holes, some of the strangest and most extreme objects in the universe. And the deeper scientists look into them, the more bizarre they become. A black hole isn't simply a giant hole floating through space. It is a region where matter has been compressed to an extraordinary density and gravity has become so intense that the normal rules of our everyday experience completely break down. Today, we're going to explore some of the weirdest facts about black holes, and by the end, you'll see why these cosmic monsters remain among the greatest mysteries in science. The first strange fact is that a black hole isn't actually a hole. Despite its name, it doesn't contain an empty tunnel leading somewhere else. A black hole is a region of spacetime where gravity has become so strong that there is a boundary called the event horizon. Once something crosses this boundary, escaping would require traveling faster than light. And according to our current understanding of physics, nothing can do that. The event horizon is therefore less like the edge of a physical object and more like a one-way boundary. You can cross it going in, but according to classical physics, you cannot come back out. And here's where things get even stranger. A black hole can be incredibly small while containing an enormous amount of mass. Imagine taking the mass of our sun and compressing it into a sphere only a few kilometers across. You would create a black hole. The sun itself is nearly 1.4 million kilometers wide, but if you somehow compressed all of its mass into a region only about 6 kilometers in radius, its gravity would become strong enough to form an event horizon. This shows just how extreme the physics of black holes really is. Their power doesn't come simply from having a huge amount of matter. It comes from concentrating enormous mass into an incredibly small region. But our sun will never become a black hole naturally. It isn't massive enough. When the sun eventually reaches the end of its life, it will expand into a red giant and eventually leave behind a white dwarf. To create a black hole through the collapse of a star, the original star generally needs to be much more massive than the sun. When such a massive star runs out of fuel, gravity can overwhelm the forces supporting its core. The core collapses catastrophically, and the outer layers can explode outward in a supernova. If the remaining core is massive enough, it can continue collapsing until a black hole forms. Now imagine getting close to one. From far away, a black hole might appear relatively ordinary. You could be orbiting it just as planets orbit stars. But as you approach, something extraordinary happens. Gravity begins affecting time. According to Einstein's theory of general relativity, the stronger the gravitational field, the slower time passes relative to someone farther away. This means that a clock near a black hole would tick more slowly compared with a clock far from it. If you were watching a spacecraft fall toward a black hole from a safe distance, you would see something bizarre. As the spacecraft approached the event horizon, its movement would appear to slow down. The light coming from it would become increasingly redshifted and faint. From your perspective, it could appear to approach the horizon more and more slowly, fading away as its light becomes stretched by the intense gravity. But for the person falling toward the black hole, their own clock would appear normal. They would not feel time slowing down around them simply because they crossed the event horizon. This leads to one of the most famous strange effects associated with black holes, spaghettification. The word sounds almost humorous, but the phenomenon is anything but. Gravity gets weaker as you move farther from an object. Near a black hole, the difference in gravitational pull between your head and your feet can become enormous. If your feet are significantly closer to the black hole than your head, they can experience a much stronger gravitational force. The result is that your body could be stretched vertically while being compressed from the sides. Scientists call this tidal stretching, but the nickname spaghettification describes the effect perfectly. Interestingly, the experience depends on the size of the black hole. A small stellar mass black hole can have extremely intense tidal forces near its event horizon. A supermassive black hole, despite containing millions or even billions of times the mass of the Sun, can have a much gentler gravitational gradient at its event horizon because the horizon itself is enormously larger. That means, theoretically, you could cross the event horizon of a sufficiently large supermassive black hole without immediately experiencing the dramatic stretching associated with smaller black holes. The real danger would come later, deeper inside. Another strange fact is that black holes can collide. Across the universe, pairs of black holes can orbit each other for millions or billions of years. As they move, they release energy in the form of gravitational waves, causing their orbits to shrink. Eventually, they spiral closer and closer together until they merge. The final collision can release an extraordinary amount of energy, briefly producing gravitational wave power on a scale greater than the combined light output of countless stars. We know these collisions happen because scientists have actually detected the ripples they send through spacetime. In 2015, the LIGO Observatory made the first direct detection of gravitational waves, produced by the merger of two black holes roughly 1.3 billion light-years away. The signal lasted only a fraction of a second, but it represented a monumental discovery. Humanity had effectively detected the vibrations of spacetime itself. Black holes can also be incredibly bright, which sounds completely contradictory. After all, black holes are famous for not allowing light to escape. But the black hole itself isn't what shines. Matter falling toward it can form a rapidly rotating structure called an accretion disk. Gas and dust in this disk can be heated to millions of degrees by friction and gravitational forces. As the material spirals inward, it can produce enormous amounts of radiation, including visible light, ultraviolet radiation, and X-rays. In some cases, the region surrounding a black hole can become brighter than an entire galaxy. Some black holes are even surrounded by enormous jets. These jets can shoot particles away from the black hole at speeds approaching the speed of light. They can extend for hundreds of thousands or even millions of light-years into space. The exact mechanisms behind these jets involve powerful magnetic fields and the rotation of matter around the black hole. In the most extreme cases, these jets can influence the evolution of entire galaxies. And then there are supermassive black holes. At the center of most large galaxies, including our own Milky Way, astronomers believe there is a supermassive black hole. The one at the center of our galaxy is called Sagittarius A star. It contains roughly 4 million times the mass of the Sun and lies about 26,000 light-years from Earth. Despite its enormous mass, it occupies a region of space relatively tiny compared with the size of the Milky Way. Even stranger are the supermassive black holes containing billions of solar masses. Some existed when the universe was less than 1 billion years old, creating a major mystery for scientists. How could such enormous black holes grow so quickly in the early universe? Researchers are still investigating possible explanations, including the rapid growth of smaller black holes and the collapse of enormous clouds of gas. But perhaps the strangest black hole fact of all is that they may not actually be completely black. In the 1970s, physicist Stephen Hawking predicted that black holes should slowly emit radiation because of quantum effects near their event horizons. This phenomenon became known as Hawking radiation. If this prediction is correct, black holes can gradually lose energy and mass over incredibly long periods of time. For a typical stellar mass black hole, this evaporation process would take an unimaginable amount of time, far longer than the current age of the universe. Supermassive black holes would take even longer. But eventually, according to the theory, a black hole could lose most of its mass and disappear in a final burst of energy. That means black holes may not be truly eternal. Even these seemingly unstoppable cosmic monsters could eventually fade away. And this creates one of the biggest mysteries in modern physics, the black hole information paradox. Quantum mechanics says information about physical systems should not simply disappear. But if matter falls into a black hole and the black hole eventually evaporates through Hawking radiation, what happens to the information contained in that matter? Does it somehow escape? Is it encoded in the radiation? Or does our current understanding of physics break down somewhere along the way. Scientists still don't have a universally accepted answer. There is another fascinating mystery surrounding black holes: what happens at their center? Classical general relativity predicts that matter collapsing into a black hole can reach a point called a singularity, where density and spacetime curvature become mathematically extreme. But physicists don't believe this necessarily means nature literally contains an infinitely dense point. Instead, it may indicate that our current theories are incomplete. General relativity works extraordinarily well for gravity on large scales, while quantum mechanics describes the microscopic world with incredible precision. But inside a black hole, these two descriptions collide under extreme conditions. A complete theory of quantum gravity may eventually be needed to understand what really happens. And then there's the possibility that black holes could be connected to ideas far beyond what we can currently test. Some theoretical models have explored wormholes, extra dimensions, and even the possibility that black holes could be related to entirely different regions of spacetime. These ideas are fascinating, but they remain speculative. There is currently no confirmed evidence that black holes are portals to other universes or shortcuts through space. The real black holes we observe are already strange enough without needing science fiction to make them mysterious. What makes black holes so fascinating is that they aren't just monsters hiding in the darkness. They are natural laboratories where the laws of physics are pushed to their limits. They challenge our understanding of gravity, time, space, matter, information, and even the ultimate nature of reality. And perhaps the most humbling fact is that black holes are not rare cosmic accidents. The universe may contain millions or even hundreds of millions of stellar mass black holes in a single galaxy like the Milky Way. There could be billions or more across the observable universe. Most are invisible because they aren't actively consuming material and therefore don't produce bright radiation. We detect many of them indirectly by watching how they influence nearby stars, gas, and spacetime itself. So the next time you look into the night sky, remember that the darkness between the stars may not be empty. Somewhere out there, invisible black holes are drifting through the cosmos. Some are quietly orbiting the centers of galaxies. Some are consuming gas in distant stellar systems. Some are merging with other black holes and sending gravitational waves across the universe. And some may be completely invisible to us, revealing their existence only through the subtle influence of their gravity. Black holes remind us that the universe is far stranger than anything humanity could have imagined. They can bend time, distort space, stretch matter, power enormous cosmic jets, merge with one another, and perhaps even slowly evaporate away. Yet despite decades of research, we still don't fully understand what happens beyond their event horizons or how gravity behaves at their deepest interiors. Perhaps that's why black holes remain so captivating. They represent a boundary between what we know and what we don't. Every discovery brings us closer to understanding them, but every answer seems to create another question. And somewhere in the darkness, millions of light years away, another black hole is quietly waiting, reminding us that the universe still has secrets far beyond the limits of human imagination.